Hello there. We've been looking at a response analysis of multi-degree of freedom systems, and I have basically looked at the overall concept, and we also looked at one example to highlight some of the issues related to analysis. I am not doing any more dynamic analysis, because as I said, since if you use the mode superposition method, and since we are only talking about linear systems, okay, if you use the mode superposition method, essentially it boils down to a single degree of freedom system problem. And if you have a single degree of freedom system problem, okay, we've solved enough about how to analyze it for different kinds of loads. However, today I am going to look again at a specific kind of load, basically because the form of the equations of motion and other associated issues become highlighted, and that is we are going to look at earthquake response of multi-degree of freedom structures. Okay? So, that in a sense is what we are going to be looking at today. Okay? So, now before I start looking at multi-degree of freedom system problems, since I looked at only earthquake response of single degree of freedom problems, what I will do is I will start off with looking at the generalized single degree of freedom and define how the earthquake response is obtained for a generalized single degree of freedom, because again it is a single degree of freedom problem. Okay. So, let us look at again just to derive the basic, let us take the cantilever, and here so this is the state of the cantilever. Okay, so this is what it is, and then I displace it, I subject it to a ground acceleration. So, what happens is at any instant of time, okay, this is the state of the structure. So, if we look at it, essentially what happens is that if you look at purely at essentially this problem becomes this. Let us look at, let us go from first principles, right. So, we look at the forces that are in the system, and so if we look at the forces in the system, one is the due to this deformation, and this deformation, as we know, is given by the following, where from here to here is given by z of t. The deformation is given by z of t, however, this part is V g of t. Okay. So, if we look at it, so this is z of t, and this V x of t which is essentially this displacement. It is always this displacement. V x of t is equal to xi x into z t. We have already talked about this, right. So, therefore, if you look at it, the m x due to the deformation is equal to E I V double prime, which is what, d squared V by dx squared, we call it as V x double prime. So, this is equal to E I into the second derivative of xi x into z of t. So, this is my m x due to the deformation, and let us look at what is the acceleration that this point undergoes. The acceleration that this point undergoes is the following. It is equal to m bar x dx, that is again the mass, times the acceleration, and the acceleration is equal to v double dot x of t, that is this part, plus because that is the acceleration. The mass was here and it is here. So, it is being subjected to that acceleration. Okay. So, if we look at this, this essentially becomes the following. I will put this as m x dx xi x into z double dot plus v g t. So, this is the due to the deformation and this is the inertial force term. Now, there are no other loads on this system. So, if I look at it from that perspective, that we have now these are the forces, and so now what I am going to do is I am going to subject this to a virtual displacement, and note that the virtual displacement is this, right. So, this is equal to virtual displacement, and del v x of t is equal to xi x into del z of t. Sorry, no del z of t, this is just del z. This is the virtual displacement, xi x into del z. So, this is this is only with x, because this is a virtual displacement. It is a virtual displacement, and what we do is we now, given this virtual displacement, we find out the work done, and we have already done this, that the work done by these m x is going to be equal to m x into, now it is going to be opposite. So, it is going to be minus m into x into what is it going to be? It is going to be equal to del v. So, it is going to be del v prime x dx. That is the relative motion of one end respect to the other, because this is an internal force, and then I have minus m bar x, and this is integrated over the whole length, because that is again for a particular infinitesimal element, and then this m bar dx into xi x z double prime plus v g of t. This is the force, this into del v x, that is, and that integrated from 0 to L. So, this in a sense is the work done by the forces, and that is equal to 0. Okay. So, now if I put this in, what do I get? Well, I can take the minus out, because I can put it on the other side, and so this becomes essentially E I xi prime. I am going to put z of t outside. Okay, so, E I is double prime, the z of t goes here, that is m x. Then del v is equal to xi x double prime del z into dx, plus I am going to put the term in here. So, this is going to be equal to m bar x dx into xi x z double dot plus v g into xi x into del z equal to 0. Now, since del z exists in both of them, essentially I can take del z outside, and then my equation essentially becomes this, that it becomes z t 0 to L E I squared x dx plus, and I am going to put the zx term outside. So, this is going to be zx 0 to L m bar x xi squared x dx, because the xi x dx this one, and this and I am going to take this term, which is the Vg term, on the other side. So, this is going to be equal to minus Vg time 0 to L m bar x xi x dx. So, this becomes the equation, and so if I rewrite it in this form, I am going to rewrite it in the following form. I am going to rewrite it in the form that m star z double dot plus k star z is equal to minus L into Vgt. This is my equation, where obviously m star is equal to 0 to L m star x xi squared x dx, k star is equal to 0 to L e I x xi double prime x the whole square dx, and L is equal to 0 to L m bar x xi x dx. Now, if I look at this, okay, this looks exactly like the single degree of freedom, excepting that in the single degree of freedom it was m z double dot plus k z m v double dot plus k v double dot is equal to minus m v. So, the only difference between the generalized is that you do not get m star over here. M star note is m bar xi squared x dx. What you get is an L, which is m bar into xi x dx. Okay. So, that is what you get, and then if I look at the solution to this problem, okay, it becomes a fairly trivial kind of a solution, because see, we already look at it. Let's look at what we have solved. We have seen that this plus, well, I mean, I can put now my C star, I mean, this one is minus m v g double dot, and what we got was that, look, v of t was equal to what was in this particular case equal to here you have minus v g double dot, okay. This is m upon k. So, what do you get? You get I m. So, you get this minus 0 to t v g tau h t minus tau d tau, and the only thing that was there was that, remember this, that what we had was that this was the unit impulse response function, and it was 1 upon m omega. Remember that this was 1 upon m omega into m. So, this thing disappears. So, what you get is essentially v of t minus 1 omega 0 to t v j tau h t minus tau d tau, and we said that the max of this was equal to S d. Okay. So, now let us look at this particular problem. Okay. This problem essentially is m star z double dot plus, well, it does not matter, c star k star z minus L v g double dot upon n. So, if you really look at it, what happens over here is that this, what will be the response of this? This one will be minus 1 upon m omega 0 to t Vg tau h t minus tau d tau, okay, and the max of this, if you look at it, okay, there will be an L here, L Vg double dot, okay, upon 1 upon m omega, and so this then becomes the solution. Okay, L comes out, so L actually comes out here. So this one, if you look at it, this part is identical to SD. So if you look at it, the peak displacement is equal to L upon m into SD. Okay, so that becomes my solution. Okay, and then of course, you know, we can find out what do we want to find out? We want to find out the shear force. Okay, the shear force, etc. we can always find out. But in essence, the point that I am trying to make is that there is a term which has been brought in where L is equal to 0 to L m bar x xi x dx and m is 0 to L m bar x xi squared x dx. Okay. So, they are different quantities because xi x is different, and although both have m bar, okay, so in a way it still is an inertial load. Okay, it still is an inertial load. It's just that the inertial load, instead of being, it's actually L upon m into m Vg double dot. So, that is the whole point, that there is an L upon m which is non-zero. Okay. In fact, L upon m, if you look at it, you will find it that it will actually land up being, it depends on the xi x that you choose, that you get different values. Okay. So, this in a sense is the generalized single degree of freedom, and I just introduced the concept of the generalized single degree of freedom to understand for you the fact that in such situations what you have is that you do not have, you know, it's still inertial loading. You know, in other words, it is still L is still an inertia term because it's m bar x dx, okay, where into xi x, which xi x is dimensionless. So, it is still a inertial force. Okay. In other words, the base motion can be transferred into inertial force, but the only thing is that the inertial force is not directly related to the mass, but to a factor L, okay, which we call as mass participation. We call that as the mass participation of, or rather the inertial participation of the load. Okay. So, this is just to illustrate the point. The generalized single degree of freedom was just to illustrate the point to you that it is not the same as that you had for a single degree of freedom system. So, now let us look at a multi-storied structure, and I am going to, as I said, you know, I am now specifically talking about plane frames. Okay. So, what I am going to define right now is plane frames, and then in the next class we will see how we can tackle the problem of when you have a building. Okay. So, this is not a building, it is a plane frame. Okay. So, so here this is, let us say V3, V2, V1. Actually, you know, I could call this Vn, you know, I mean, because it can be an n story building. Okay. And this, if we look at any inertial point, this is the inertial system. Okay. Now, it is subjected to, so this is also the inertial point that we have. Now, due to base acceleration, what happens? This moves here. So, I am going to look at this as the shifted inertial frame, and due to the base, this actually starts going So, you have what we call as V1, V2, V3. Now, V1, V2, V3, the way they are defined, so this V of t is actually displacements relative to ground. Okay. So, this is how we define the displacements relative to the ground. If we define the displacements relative to the ground, okay, in other words, the ground has moved here. So, the displacements are all considered relative to the ground. Then what do we have? Well, let us look at it. This is M1, M2, M3. Okay. So, if you look at the inertial force, okay, what we have is, if you look at this particular thing, you also have a V total of t. V total is the total displacement at the point. So, this is the total displacement from here to here. That is called as V total 1, this is V total 2, this is V total 3. Okay. And if you look at it, the masses are being subjected to these accelerations. So, they are being subjected to the relative the accelerations. So, then what you have is m into V total, okay. That is the inertial force, plus now k, because that is the deformation, into V is equal to 0, because there is no external load. Okay. However, if you look at this, what is V total t equal to? It is equal to the relative plus everywhere is the same. So, it is equal to V g t, but 1, right, because V g t is a scalar. So, it has to be 1. So, if you look at now this is the equation of motion, because this is the inertial force and this is the spring force and this is equal to 0. We are assuming that there is currently no damping. Okay. So, therefore, if you look at it, we get this kind of a situation, that since V total is equal to V of t plus, now each one is being subjected to, this is a vector of 1s into the ground acceleration. Every one of them is 1, 1, 1, and so this is a vector of 1s. Okay. So, if I look at m v double dot t plus k v is equal to 0, this becomes then m v double dot plus m into 1 dot v g t plus k into v is equal to 0. This is a n by 1. So, I will take this one on the other side. So, my equation in terms of the displacement. So, what we have here is minus m into 1 into v g. Okay. Note that this then becomes the equation of motion at the where note that V of t is displacement relative to ground. Please understand that this is a displacement relative to the ground. Okay. So, if this is the equation, so this becomes our basic equation, and then what we do is, what do? We say that, look, okay, this is like a loading, right. So, we have a situation where we have m v double dot plus k v is equal to p of t, where p of t actually, if you look at it, okay, this is a vector, okay, the P of t is nothing but minus m into a vector of 1s into V g of t. Okay. So, this is an n by 1, this is an n by n, this is an n by 1 vector of 1s, all of them are 1 and this is a scalar. Okay. So, this note that this is what you get, and if P of t is this, okay, if I look at the mode superposition method. Okay. So, I am going to look at now solution using mode superposition method, because I am looking at linear systems only. So, if I look at mode superposition method, what do you get? Well, you see the basic point then becomes is that I have found out P of t, I know what the modal amplitude equation looks like. Okay. So, the modal amplitude equation looks like m n y n double dot, and here I can incorporate my damping y n double dot plus omega n squared y n, okay, is equal to P n of t, where what is P n? P n, if you look at it, is nothing but P n of t is equal to phi n transpose P of t. Okay. This is 1 by n, this is n by 1, this is 1 by 1, okay, scalar. Okay. Now, here in this particular case, P n of t, P of t is equal to, so I am going to say phi n transpose, I am going to put this as minus m into 1 into V g of t. Okay. So, this becomes my P n of t, okay. And if I look at this, this is a 1 by n, this is a n by n, this is a n by 1. So, we do get a scalar. So, this is a scalar, and this term we call as Ln. Remember yesterday when I solved that specific problem, remember I had defined that the base shear was given by Ln. Okay. So, this same phi n transpose m into 1, this is Ln. Okay. This is the same Ln that we defined yesterday. So, if you look at it, then the equation at the nth level becomes what? 2 xi n omega n m n y n dot plus omega n squared y n is equal to minus Ln into V g dot. This is what we get, and so therefore, okay, where Ln is equal to phi n transpose m into 1. Okay. So, if you look at this, this is identical to the single degree of freedom, excepting that there is a term. So, if I rewrite this, this becomes y n plus 2 xi omega n y n dot plus omega n squared y n is equal to minus Ln upon m n V g double dot. Okay. And what is this Ln upon m n? This is very interesting. See how why I did the generalized single degree of freedom. If you look at m n, it is equal to phi n transpose m phi n. In a way, you can look at this. This is like the two together, and Ln is equal to phi n transpose m into 1. Do you see the correspondence between the generalized single degree of freedom? There what did we have? M bar x xi x dx, okay. So, xi x into 1 dx, and the m star was m bar x xi squared x. So, exactly the same kind of concept, and all that we get is, if I want to look at y n max, what is my y n max? If you look at it, y n max is nothing but Ln upon Mn into Sd, which is a function of omega n and xi. Okay. In terms of the displacement spectrum, your Yn is equal to what? Ln upon Mn into Sd, because in the previous case we had said that V max was equal to Sd. Okay. So, since this is being multiplied by an Ln upon Mn, it is just that factor continues. So, this in a sense in terms, so I can get the maximum modal amplitude in terms of the deformation spectrum. Only thing is the deformation spectrum is now multiplied by a particular additional term. Okay. Now, what does this mean in terms of V n max? What is V n max? V n max is nothing but the contribution of the nth mode to the displacement. So, if I look at V n max, this is nothing but phi n into y n max. Okay. So, if you look at this, then V n max is nothing but equal to Ln upon Mn into phi n Sd omega n xi. Since we typically take the same xi value across the modes, I am not putting xi n, it is xi. Okay. So, this in a sense is the peak displacement in the nth mode. Now, can I find out? So, this is a displacement pattern that we have. And by the way, this is relative to ground. Please note that. So, this is just the essentially the deformation of the structure is what we are looking at. Okay. And so, if this is the displacement pattern, we also again say what displacement pattern gives this, what force gives this displacement pattern. And so, if we look at that force Fs n max, so that this is the spring force or rather the force that is going to give rise to this peak displacement. So, if you look at it, this is going to be equal to what? It is going to be equal to k into V n max. Do you agree to that? Right? Okay. So, now this is Fsn, because this is the load that statically gives this displacement. So, this is the load. So, if I put k into Vn, I am going to substitute that term for Vn in here, and if I substitute that and look at that particular thing, what do I get? I get Fsn max is equal to k into Ln Mn, which is anyway outside, phi n into Sd omega n xi. I can take these factors Ln upon Mn and Sd n, I will call that Sd n because it is for omega n, and take those as scalars and keep this k phi n in here. Okay. So, what is k phi n equal to? It is equal to Sdn. K phi n is equal to omega n squared into m phi n by definition, right. This is k phi n is equal to omega n squared m phi n is by definition, we have already seen that. Okay. And so, therefore, this thing again becomes a scalar, and if you look at this, what is omega n squared Sdn? It is nothing but San. So, it is Lan Sdn omega n squared, remember it is a pseudo acceleration velocity. So, that is Sa omega n xi, and this is the parameter, and this is being multiplied by m phi n. That is the load that you have. So, if I were to draw this, that means in the nth mode, okay, I have this structure, and again I am just saying that I have at all corresponding to all degrees of freedom, and Fsn, Fs2, Fs1, these are the loads that I have. So, if I look at the base shear, or rather not time, the max, because these are all in the nth mode. So, this is going to be the base shear in the nth mode and obviously maximum. Okay. What is that going to be equal to? That is going to be equal to 1 transpose into Fsn max. Okay. So, what is that equal to? Plug in Fsn max, what we get is ln upon mn into San, I will call it again, into 1 transpose m phi n. We have already done this, phi n transpose m transpose into 1 transpose transpose. M is a symmetric matrix. So, m transpose is itself. So, this becomes nothing but this we have already seen is equal to ln. So, if you look at Vbn, what do you get? Ln squared upon Mn into San. Such an elegant formulation for the base shear due to earthquake load. Okay. So, therefore, okay, what we have finally done is in the nth mode, this is equal to ln upon mn s omega n xi into phi n. So, this is my displacement. The equivalent static forces in the nth mode is equal to Fsn max, which is equal to ln upon mn into Sa omega n xi n is m phi n. These are the equivalent static force, and you can actually apply these loads on the structure and get every other force response or displacement response or rotation, what have you, you can get all of those. Okay. Because note that in the nth mode, nothing is varying with time. So, this is a specific thing, and then finally, Vb, the base shear in the nth mode, is given by ln squared mn into Sa omega n xi. So, everything, and I will write down on top, yn max is equal to ln upon mn into Sd omega n into xi. Of course, every term will be different for different modes. Okay. The problem that we have here is that, and this is the point that I wanted to make for this particular thing, is that we can get every displacement in each mode, the peak value in terms of the response spectrum. The only thing is that here for each mode, since it is omega n xi, so for each mode the value of Sd and Sa are different. You have to take that particular omega n and then take it. So, if we look back at something that we had looked at earlier, and if you look at this, we'll just go back to the original thing that I had done. Okay. This is the time history, this was the deformation, this is the velocity, this is the acceleration. Okay. So, if I want velocity, let us say displacement, what do? Well, I actually take this, right. So, now here you have Tn, okay. If it is omega n, there is Tn. Tn is equal to 2 pi upon omega n. Okay. So, Tn, so let us say you want the first mode, you find out its Tn and read out the displacement value. If you take another mode, if you want to take here, so let us say that you are the first mode, let us say first mode, first mode frequency is low, okay, so time period is longer. So let's say the first mode is let's say 3 seconds. So you go up here and let's say you have 5% damping. So you take over here and you see that the displacement SD, okay, there is no displacement, this is SD. SD is like say 260 millimeter. Okay. So what you do is you take this over here as 260 millimeter for the first mode, okay, and then you find out L1, M1 and Phi1 and you've got your V1 max. Okay. Then you go to let's say the second mode. The second mode let's say is like 1.5. Okay. So if you take it as 1.5, we come here and we see 100. So for the second mode, this is first mode, this was 260, and for the second mode, this one is first mode, this is 260, for the second mode, this is 100, and you have L2, M2, and you can find out the V2 max. Okay. So the displacement in the second mode, you can find out the displacement in the first mode in this way. Similarly, if we go here and we look at the pseudo acceleration, so we say that look 3 seconds, okay, so we go back over here and take it and we see it's like 0.18. So in the first mode, this is going to be SA is going to be equal to 0.1 G, which is 1 meter per second squared. So this becomes 1, and so these are all the things that you have, and or this is 1 meter per second squared, and this you get, and you get this particular for the first mode. For the second mode, which is let's say 1.5, I'll come over here, look at it, and I'll see, oh, okay, it's about 0.2. So I take this as 0.2 and similarly go through with the procedure. So you understand the basic concept that here that you have is that this value and these values depend on omega n. Okay? So that's the key point, that for different modes, you have different values of SA and SD, which you read off, for the particular value of omega n. Okay. But ultimately what happens is that look, what we have here is, let's say, in a way I am calculating V1 max, V2 max, V3 max, right, and so on and so forth up to Vn max. Okay. Or I say VB1 max, VB2 max. So let me just say that here also in this particular vector you actually have particular displacements, let's say top story displacement, or so you can read it off. So if I say any response quantity I am getting Rn, the peak response, because I am using response spectrum. Okay. If I was using the time history, okay, if I was using the time history and I found out, for example, let me just go back here, and if I was looking at time history, Vn of t, okay, would be equal to, well, this would be equal to Ln upon Mn into phi n into, and this one would be like minus 1 upon omega 0 to t Vg t tau Ht minus tau, which is the unit impulse response function. Suppose we found out Vn in this way, okay, then Vbn, okay, t would nothing be Ln squared Mn into omega n squared into minus 1 0 to t Vg double dot Ht upon tau. So all of those kinds of things, you evaluate it. Okay. So what you do is, if you get the time histories, then there are no issues, because what? If you look at it, this is already phi n yn. So if you look at it, then V of t becomes just summation Vn of t, n going from 1 to n. Okay. Similarly, any response quantity, okay, I could put it this way, that if I had the time history, any response quantity would be equal to summation n going from 1 to n, okay, R n of t. Note that this is valid. Why? Because at any instant of time, I can always add them up. Okay. The problem that I have for this particular problem, when I have maximum, when I am using the response spectra, and I am using the response spectra, what happens is I only get max values in every mode. Now, one of the things that you could say is that, well, so what? Could I find out, for example, R max is equal to summation n going from 1 to n R n, where R is any response. Could I say that? You see, the problem with this is that although this is valid for any instant of time, for this to be valid, what would happen? All R n max would have to occur at same time, right? So, this mode superposition, although it is valid when you are doing time history, because at any instant of time, okay, you can add up, yeah, you can add up, okay, but if all of them would have occurred at the same time, okay, then this would be valid, okay. Otherwise, this is not valid. And typically, what happens is any response quantity, okay, if you look at it, if you look at the time history, look at the time history, okay, look at VBN of t, okay, you will typically see that what essentially shows up in each mode is going to be its own frequency. You will see, you know, when you do it, you will see that you essentially get the same frequency. And the peaks, you know, the fundamental aspect is that the peaks, and this maximum value is nothing but the peak in each mode will occur at its own time. They do not occur at the same time. So, in other words, when I say VB1 max, this is occurring at say time t1, VB2 max will occur at some other time t2, and in that way VBN will occur at some other time tn. Now, what are these? We have no clue. These depend really on the acceleration time history of the ground acceleration time history, because obviously you know, where the peak occurs will depend on the time history, and also the you know, the frequency of its own. We have seen all of these, you know, in the single degree of freedom. So, I don't want to go into that. We do know that the peaks will not occur at the same time. What happens when peaks don't occur at the same time? If peaks don't occur at the same time, then we have to do what are known as modal combination rules. To combine the modes, we have to use rules. Okay. The one that I showed you, which was R max is equal to N1n into Rn max. This is known as absolute sum rule. Okay. Then you have R max equal to n going from 1 to infinity Rn max squared square root. This is known as the square root of the sum of the squares, square root of the sum of the squares, the SRSS rule. Okay? This is the SRSS rule. Okay? And there are various other rules. I will talk about these rules in the next class. Okay? So, just to tell you that earthquake response analysis you can do in two ways. Time history analysis, there is no problem. Okay? All that you have is that yn of t is ln upon mn into the single degree of freedom solution. Okay? And then Vn of t becomes equal to phi n yn, and then you can always sum up any displacement quantity, the equivalent static force Fsn was equal, we showed it to you that it was equal to ln upon mn into m phi n omega n squared into the displacement yn. Okay. So, all of these kinds of things can be done if it is time history. We also developed what is known as the response spectrum method of analysis. And this response spectrum method of analysis, we show that you have to use modal combination rules. I will keep talking about this in the next lecture. Thank you very much. Bye-bye.